All right, welcome back on the next lecture. So this lecture is we're going to talk about this concept called constraint optimization. And ideally, you should know how to do regular optimization already, implying that you can take derivatives with respect to matrices as well as vectors. So these are the topics we're going to cover. This is a course at Northeastern University, and I'm Professor Wu. So let's get started. So basic optimization. We have previously learned the general idea. So when we have an expression that looks like this, essentially what it's saying is that we want to find the W that makes this expression, right? So W is the variable, everything else is a constant. We want to find a W such that when we plug it in, this whole thing, which is a value, is as small as possible. That's what minimization is, and we've done this several times. And it's straightforward if you can find a closed form solution. The idea is we take the derivative and set it to zero, and that allows us to essentially um, find the closed form solution for this. Okay. And this type of problem, which we've seen many times, is called unconstrained optimization. So we're trying to do optimization, which is W, that makes this as small or large as possible. And there are no additional constraints. Okay. And we can solve this with closed form or we can solve it with gradient descent. Now, today, we're going to start at making this problem a little bit more complicated, which is called the constraint optimization. An example of that would be you're trying to minimize this, and ST, this is subject to, so it's subject to some kind of constraint that W times a one vector equals to one. So if you picture if W is two dimension, it could be more than two, multiplied by 1 would be W1 plus W2 equals to 1. So this is telling you that you can find the solution that that makes this expression as small as possible while this constraint W1 W2 has to add up to 1. Okay? So this must be satisfied so you're trying to do two things simultaneously, satisfying this and finding the solution that makes this expression as small as possible, right? That's why we call it constraint optimization. This condition here is constraining your possible solutions. Previously, you can just pick any W that makes this as small as possible, but now you have to satisfy this as well. Okay, that's why constraint. Now, there are different kind of constraints. There's the equality and inequality constraints. Over here, the one we just saw is an equality constraint because it has to equal to something. So here's another example. You're trying to minimize this, right? Where here are the constraints. This is called inequality constraint. That x times x has to be less than 5, right? So there's an inequality. And the value x1, x2 has to be greater than 0. That's both of these are called inequality constraints. Right? And then an example where b times x has equal to 4 and b is equal to this. So this is an equality constraint. It's saying that this has to be true with the equality. So with constraints, you can have two types: equality or inequality. Right? Now, inequality that's greater than or less than are basically the same because if you just put a negative in front of it, then it converts from greater than to less than. So in general, we convert everything to less than 0. Like that's the standard we tend to use. Okay, so we've actually at this point already seen couple constraints. So one example was PCA and LDA, which we've done them before. The real problem was posed such that you're trying to maximize some kind of objective that looks like this, such that this is a unit vector, right? So this is really a constraint, right? So so the most general form of the constraint problem looks like this. You're trying to find the x that minimizes this function f of x, subject to bunch of inequality constraints. So the inequality constraints, we tend to represent them as G. So G1, G2, G3. You can have multiple of them. And then H is the equality constraint. Similarly, you can have multiple H1, H2, H3. These you can have multiple equality and multiple inequality exams. So at this point, um, give it a try. I mean, obviously I haven't taught you how to solve them, but see, just take a moment and see if you can figure out ways which you can solve this. Okay, just take a couple moments. If you can't figure out, then we'll move on. So pause the video, think about it, see if you can find a way to solve this. Okay. All right. So let's move on. Well, to solve this problem, well, one way to solve it is start by saying that, well, we have an equality constraint. This has to be true. Okay, no matter what, this one has to be true. If this is true, then we can represent this expression in terms of x1. So I can move x2 to the other side, which give us x1 is equal to this. And now we can rewrite this expression in terms of x1. So here, right, x1. Remember, I just said x1 is equal to 1 minus x2. So we can plug this into x1 as 1 minus x2, right? And if we multiply this out, we end up with a term that is only in terms of x2. Notice there's no more x1 because, well, we plugged it in. And then when we simplify, we have a pretty simple expression. We have an expression in terms of x2. So if we want to do minimization, we can simply take the derivative and set it to 0. Okay? So the derivative of this is 6x2 and minus 4, right? So if we take the derivative and set it to 0, this tells us that x2 must equal to 2/3. So now we know x2. If we know x2, the optimum x2, since x1 plus 2/3 is equal to 1, then x1 must be 1/3. So we just solve x1 and x2. So that's an example. That's an example how you can solve it this way. Okay, so 1/3. Well, another way to solve this could be you just randomly generate numbers. Here, I keep randomly generate x1. And x1 is a value between 0 and 1. So I keep generating them. And then, since x1 and x2 has to add up to 1, I once I generate x1, I generate x2. So now we know that x1, x2 has to equal to 1, right? Because I generated it. So I just randomly generate them. Randomly generate them. And after that, I plug the value x1, x2 inside the function. After I randomly generating them, I plug them. And if this u value, right, is less than the previous one, so I start with some very large number. If it's less than, which we're trying to minimize, so we're constantly looking for a lower one, then I'll print it out. I'll print out the result. So what it's saying is that we're just randomly picking x1, x2, and we keep the one that give us a lower and lower and lower result. And you can see every single time I print it out, the result gets lower, 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 lower. And you can see that the final result is approximately 2/3. So 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 basically that is the point, is you can just plug in random numbers that happens to match the constraint and then find the one randomly that gives you the best result. So you can solve it this way, very crudely. This is very simplistic methods. Simplistic. And this is just like raw computation. You just keep generating numbers and you keep finding ones that's lower. And this could take a long time, right? Long time. Notice I ran it for 3,000 times. So this could take a while for you to find a good solution. So, okay. So here. These are the two ways. But of course, I'm not recommending these two ways. These are the two ways which you can use just right now if you didn't learn anything new. Okay. Now, in terms of optimization theory, the standard way we actually go about solving constraint optimization is through this thing called the Lagrange multipliers. Okay, the idea is that you will add constraint into the objective. So, so like for equality constraints like this, right? So here's the equality. That was the constraint we were working with. So when we are dealing with Lagrange multipliers, what we do is we rearrange it into a standard form. The standard form is equal to zero. So you just rearrange it so whatever expression is equal to zero. And once you have this expression equal to zero, we add this directly into the objective. And the objective, right? So here is the objective, here's the constraint. And after you add it in, notice how this right here is equal to this. So we create a new objective. And this objective, part of it is the original, and part of it comes from the constraint. This right here, addition, gives you a new function, and this new function is called a Lagrangian. Lagrangian. And this is what we will solve. This is what we're going to look at after. And we add, notice we add an extra variable. This variable is called a Lagrange multiplier. Lagrange multiplier. So notice how we start with objective, constraint. Now we only have one single function. We've combined the constraint directly into the objective, along with a Lagrange multiplier. Now, at this point, when you just create this, you have no idea what this number is. You can pick one that might work, or you might not. So we're going to talk about how we go about finding this number. Okay. So how Lagrange multiply impact the solution? So over here, remember I converted into a Lagrange multiplier. So Lagrangian. We convert, and that we have a Lagrange multiplier. So how does the Lagrange multiplier lambda impact our solution? That's the question here. Now, how does it impact? Well, let's assume first that the Lagrange multiplier is zero. What happens? If it's zero, this is not there, right? None of this is there. So we can just take the derivative and set it to zero. If we take the derivative, set it to zero, then what's the derivative of this? For oh, that should have been 4x1. I did that wrong. Okay, mistake. And then over here should be 2x2. Okay, so that right there is good. And regardless, if we set this to zero, the optimal x1, x2 is equal to zero. Right? So notice we take the derivative, set it to zero, and therefore it's saying that if we ignore the constraint, then the optimal is simply 0, 0. And the lowest you can get is 0. That's what it's saying. Well, unfortunately, 0, 0 may make this as low as possible. It does a good job of that, but it did a poor job satisfying the constraint, right? So the constraint is that these two add up has to equal to 1. But if you have 0, 0, that's equal to 0. So 0 is obviously not equal to 1. So we got, if we pick 0 for lambda, right, then it's saying that the optimal solution for x1, x2 is equal to 0, 0. And since x1 plus x2 is not equal to 1, instead it's equal to 0, the difference between what we got and what we won is 1 versus 1 minus 0 is 1. So we have an error of 0. So we're supposed to get 1, but we got 0. Therefore, there's an error. So 1 minus 0 is equal to 1. So the point is, previously, the difference between what we won and what we got is 1. And we're going to call this error of 1. All right. Well, so that's when we use Lagrange multiplier as 0. What happens if we increase a little bit? Let's increase it to 1. Well, if we increase it to 1, then it'll be a 1 here. So that's just a 1, resulting in something looks like this. So this right here came from the constraint, right? This is the constraint. This right here is the function itself. Okay, so we pick one. What happens now? Well, if we take the derivative again, this would be 4x1 minus 1, 2x2 minus 1, right? Now we take the derivative, set it to 0. If we set it to 0, then x1 x2 is equal to 1/4 and 1/2. Okay? Okay, so this also minimizes this objective. And let's see if it does a good job of satisfying the constraint. Well, 1/4 plus 1/2 is equal to 3/4, which once again is not equal to 1, right? We want them to add up to equal to 1. However, the error is much smaller now. Previously, we got a 0, but now we got 3/4. So the difference between 1 and 3/4 is equal to 1/4. So we got a much lower error. Therefore, you can kind of see that by playing around with the Lagrange multiplier, we can keep moving it until we got to a point where the error is 0. Right? We can keep playing with this until we got to a point that we got basically satisfies the constraint and make this as low as possible. Okay. Now let's try it again. This time, instead of 1, let's make it a little bigger. 4/3. So 4 1/3. Okay. Now, what I want you to do is basically follow everything I just did. All right. Except use 4 1/3 as lambda. And then see if the constraint is met now. Right. Now, the point of this exercise is realize that there exists a lambda value. You can just keep playing around with the lambda value. So eventually, it will meet all the constraints and minimize the objective. And this is the intuition we develop for this thing called the KKT condition. But for now, pause the video and see if you can solve this. But this time, use 4/3 as the lambda value. Okay. All right, pause the video. I'm going to go on. Okay, so what happens if we use lambda as 4/3? Okay, well, if lambda is equal to 4/3, we're going to plug 4/3 here, right? And if we take the derivative becomes this here. This is the derivative, implying that when we solve this for equal to 0, x1 x2 is equal to 1/3 and 2/3. And guess what? 1/3 plus 2/3 is equal to 1. So the constraint, the addition that they have to be the same is satisfied. So we satisfy this constraint. Okay? And if we plug 1/3 and 2/3 into this expression, so it says that 1/3 and 2/3 into this, it gives us 2/3. So basically, it's saying that the lowest possible value you can achieve for this function is if you use 1/3 and 2/3, and you will get 2/3. So this is equivalent to what we saw before, right? When we were just randomly printing out, the value. It says that the lowest possible value was roughly 2/3. Right? You can see that. So this right here kind of confirms our intuition that this function can only go as low as 2/3 if you're trying to satisfy this condition. Okay? All right. Let's let's go on. So this kind of tells you that if you want to solve the constraint optimization and solving for the Lagrangian, you kind of need to get lucky to find lambda, right? And that's not good. You don't want to need to get lucky to find the lambda. You know that by setting the lambda, you can achieve everything you're looking for, but you don't want to be playing around with it. So so we were looking at like um so um there's another way to go about doing it besides just playing around with the number. Okay. Now let me now formally define the problem. So the problem is basically saying that we are trying to minimize some kind of function. Okay. And this function, we need to find the x that makes it as small as possible. And that there's a set of inequality constraints. The inequality constraints, we're going to always set it to be less than zero. Okay. Every inequality, no matter how it's set up, we're going to rearrange them into this. And the equality constraints, you can also have multiple of them, right? So we're going to make sure each equality constraint is also set to equal to zero. Okay. Once you do that, the Lagrangian is defined as the function plus the set of equality and a set of inequality. And these lambdas and these gammas, they are essentially the Lagrange multipliers. So you can see that in our very simple case, we only had one equality Lagrange multiplier. But once it gets more complicated, you end up having multiple. You're going to have a giant list of Lagrange multipliers. And therefore, it could be very, very hard to find lambda because you're not finding just one lambda. You're finding some combination of like 10 lambdas, 100 lambdas. So it could get really complicated. And you do not want to be randomly picking lambda to essentially keep solving the problem over and over again. Okay? So, so note the convention. Inequality constraints always ends up with less than zero, right? No matter what, 5x less than 7. You can always set this up to be less than zero, right? Notice how it's less than zero, right? And if it's 5x greater than 7, then it's equivalent to 0, 7 minus 5x, right? So you can always set it up, there's a 0. Equality constraint, you also always set it up. So that's the key standard you have to get used to and remember. Okay? So 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 then in the end, we're trying to solve some kind of Lagrangian. And the standard way to solve this kind of problem is called the KKT condition. Okay, you need to basically know and memorize the KKT condition. The KKT condition was invented by the Karush Khan Tucker, hence KKT condition. And it says that if we do have this problem, which we just defined, remember g is always less than 0 and h is always equal to 1, right? Which can be written into a Lagrangian. KKT condition says that in order for you to find the optimal, we use the concept of a star, right? The optimal x, optimal gamma, lambda. This is the best solution with the star. So in order, given this is the solution, right? Then the Lagrangian, then four conditions must be satisfied, no matter what. So if you basically go use these four conditions, it guides you to find the solution. The first is that stationary condition. The stationarity condition says that the derivative has to equal to zero, which is not a big stretch, right? You want the derivative to be zero because that tells you where the optimal is. And there's a second one, it's called a primal feasibility. Primal feasibility says that all the constraints should be satisfied. So that's not so surprising, right? If this it's saying that when you solve the problem, every single equality constraint should be satisfied. Every inequality constraint should be satisfied. Right? So first, it's saying that the derivative has to equal to zero. Second is saying that all your constraints that you have has to be satisfied. Okay. And then you have this thing called the dual feasibility. It's saying that for all the inequality constraints, the value must be greater than or equal to zero. So you can't have negative for this, right? This cannot be negative. It always has to be a positive value or zero. So that's called the dual feasibility. And the last one is called complementary slackness. So G, remember, is the inequality constraint. It's saying that no matter what, when you have an inequality constraint, either the inequality constraint has to equal to zero or lambda has to equal to zero. It's saying that no matter what, when they multiply with each other, this final result is equal to zero. These four constraints, I mean, these four not constraints, conditions, KKT conditions, allows basically guides us how to find optimization problem and solutions. And I'll show you a couple examples what I mean by that. Okay. Now, if we're trying to solve the same problem with KKT condition, right? So previously, remember we solved the problem multiple ways. One is like we plugged it in, other one we just randomly generate numbers. Now, this time, let's see how much easier it is to solve the same problem with the KKT condition. So if we try to solve the same problem, but remember, we don't know what lambda is, right? We in the end, I mean, we found 4/3 equals lambda. But let's assume we don't know that yet. Okay. So what we do first is we convert it into Lagrangian, and then we'll use the KKT condition to help us solve it. Okay. So this is our problem. And remember, after we convert it into a Lagrangian, over here is the equality constraint, and over here is the function, original objective that we're trying to minimize. And over here is the Lagrange multiply. So we don't know what this is. We don't know what this is. We don't know what this is. How do we go about? Well, the first thing we do is, well, we can use the stationarity and the primal feasibility. So stationarity says that, well, if you just take the derivative of the Lagrangian, let's take the derivative of the Lagrangian and set the derivative equal to zero. That was remember the stationarity condition. You just take the derivative and set it to zero, and the derivative should equal to zero. So now we got it. We take the derivative. Notice how it's equal to zero. So right here, that give us these conditions. This has to be true. Okay. After this, now the second one is called the primal feasibility. Primal feasibility says that the condition here we only have equality has to be true, right? So okay, so this was our condition. This our condition. This has to be true. So now notice how this is 4x1 plus 0 minus lambda. We can write that as 4, 0 minus 1 because when we multiply by x1, x2, and lambda, that's our solution. And over here, 0, 2, and minus 1. 0, 2, minus 1, right? And the very last one is this one. X1 plus x2 is equal to 1. So now we have a situation. We have a situation where we have three equations and three unknowns. And this right here is equal to ax plus y. We just have to solve for x. And we've done this in the past, right? If you know how to find the a inverse, a x equals to y, then equals to a inverse y. Then you have your problem to solve. So this essentially allows you to directly solve for x1, x2, and lambda, right? So remember, like this portion came from our stationarity condition, and the red portion was from the primal feasibility. And since we didn't have inequalities, right? Inequality constraints are specific to dual and complementary slackness. So we didn't really need the two of them. We simply solved this. Okay. So this problem here, there are many ways to solve it. You can just use the inverse, right? That's one way. You can use this thing called the RREF, which is also doable, gradient descent, or you can just numpy solver. And in the end, notice how we got the same solution. 1/3, 2/3 was the optimal solution, and 4/3 was the optimal lambda. So this right here allows you to solve like the same problem without randomly picking lambda over and over and over again. So that this is basically how the KKT condition helps you. Okay. All right. Now, why don't we pause the video? Pause the video and see if you can use that exact same problem, the way we solve it, and see if we can solve this one. Right. Use the KKT condition and see. And you can use the numpy to solve it, or RREF if you know how to use the RREF method. Okay. So pause the video, solve this. I provided the solution here, right? So if you don't remember, I provide a link here as well for you for various lectures that shows you how to do the REF. Okay. So for this one, once again, the step is pretty simple. You basically make sure you find the stationary condition, right? So the stationarity condition gives you these conditions. And then you adding the primal. Once you add the primal in, then once you add the primal in, then you end up with ax equals to y, and you can solve this with REF. If you solve it, this should be a solution. Okay, so this is a very simple example of it, where you can simply plug it into a 3 by 3 matrix and solve everything. All right, so it gets a little bit harder when we start working with inequality constraints because you need to not just use two KKT conditions, you need to end up using four of them, and that really complicates things, right? So here we have a parabola, right? X squared. We're trying to. This is x squared. So we have a parabola, and it's subjected to both an equality and inequality constraint. Okay, so if you have an inequality constraint. Notice I already set up the inequality so that it is always less than zero, right? The inequality has to set less than zero. Okay, so well, let's see. Well, this is the Lagrangian, which we have the function itself, the equality constraint. Notice this is equality, and the inequality. So remember, the equality constraint always use lambda. Inequality always use gamma. Okay, and you have multiple of them. You'll be lambda one, lambda two, lambda three. You have multiple inequality. It's going to be gamma one, gamma two, gamma three. But here we're looking at a pretty simple one where there's only one, like of each, one equality, one inequality. So what do we do? Well, the first thing you can do, walk down the list. The first thing is stationary condition. If you find the stationarity condition, then then this has to be true because you take the derivative and set it to zero. The next one is called a primal feasibility. Primal feasibility says these has to be true. Okay, so it's saying that this has to be true and this has to be true. Okay. Now, the next one is the dual feasibility. The dual variables, it's saying that all the gammas, this has to be greater than zero. So we now know this is greater than zero. And the last one is complementary slackness. It says that when you multiply the two of them, they have to be equal to zero as well. So this has to be greater than or equal to zero, and together they have to multiply to equal to zero. Okay, so let's follow this logic carefully. How do we use these set of conditions to guide us to solve the problem? Well, the first primal feasibility, right? It implies that if this has to be true, then we can divide this equal to this, right? We can split them up. If this is true, this it implies this. Now, this means that x must equal to -1 or 2, right? That's it has to. Like that, you kind of don't have other choices. So if x is equal to one of them, we have a second condition. It's saying that x is less than 0. Well, if that's the case, then it can't be this one. Therefore, we basically solve x has to be equal to 1, right? X has to equal to, -1, right? Okay, so we now know what x star is, which is -1. Now we can use complementary slackness. So it's saying that when you multiply the two of them, it has to equal to 0. So gamma times x has to equal to 0. And since we know what x is, the only way this can be true is that gamma has to equal to 0. So we now also know gamma. Okay. Now, leaving lambda is the only thing we don't know. We don't really need lambda, but let's just solve it for sake of solving it. So if we want to find lambda, well, if we know x, and gamma, right, then we basically can solve for lambda. This is the only unknown term in this. So we can now solve for lambda as well. And lambda turns out to be -2/3. So notice how by using these conditions, you can step by step by step, logically step through how, like, what the optimal solution must be. Okay, so this takes quite a bit of practice. Like, obviously, when you watch somebody else do it, it's different. They already done this many times. But when you yourself are doing it yourself for the first time, you need to like really think about, okay, how do I combine multiple logic so that you can come up with a solution? Okay. Now, the activation of inequality constraint give us the complementary slackness. So you we now need to introduce this concept of activation. So sometimes um what we just saw here, right? What we just saw here was that x is equal to -1, right? That's what we said. X is, and therefore the condition that x is less than 0 is not activated. Like, the solution is already this, right? So since we know the solution is equal to this, then gamma had to equal to 0. So activation is when the solution, let's say x star, if our x star happens to be equal to 2, right? Let's say -1 wasn't an option and it has to be equal to 2. Well, if x star happens to equal to 2, but x has to equal to 0, then this is activated to constrain this. And whenever a inequality constraint is activated, right, it pushes the solution to the boundary. It implies that x star cannot equal to 2. Instead, x star, the closest value to 2 is equal to 0, right? So therefore, inequality becomes equality when you activate the constraint, because, well, it's the closest possible solution. 0 is the closest possible solution to 2. All right. So this is what I mean by activation. And in this particular case, it's inactivated because it's already satisfying this. However, when it is not satisfying the insatisfying, the inequality constraint, then you activate the inequality constraint to constrain it. And when you constrain it, well, it has to be below here, and you're at 2. The closest thing to 2 is the condition itself, which is 0. That's when you then convert the inequality constraint into equality constraint. Then you automatically know x as well. Okay, so that's the idea of activation. So solving the following constraint using the KKT. So let's look at yet another example. Over here is saying that x is less than 1. And this is what you're trying to minimize. So the Lagrangian equals to this, right? Gamma, remember, we need this to be always less than 0. So x minus 1 is less than 0, right? That's how we got this. So this right here is our Lagrangian. And once again, we follow the 4 conditions, which you will need to memorize for the exam. The stationarity condition, you take the derivative, set it to 0. Feasibility condition. The feasibility condition says this has to be less than 0. Okay, that's the first, the conditions. Dual feasibility says that gamma has to be greater than 0. So that has to be greater than 0. And complementary slackness says when you multiply them together, that has to equal to 0. Okay, so whenever you have an inequality constraint, you want to start by looking at whether this is activated. Okay, so let's see if it's activated. The way we check if it's activated is by just solving this, ignoring the inequality constraint. So let's say there is no inequality constraint. So the solution for this is 2x squared plus 1. And then, so this is the function. We take the derivative, df dx, which is 4x, set it to 0. It's saying that x star is equal to 0. So 0, it's saying that 0 is the best solution if you ignore the constraint. And now that you know that 0 is the best solution if you ignore the constraint, let's look at the constraint. Well, it turns out that the best solution already satisfied the constraint, right? Zero is already less than one. So when it's satisfied, it tells you that you can ignore it because it's already satisfying. You don't need this inequality constraint. That's when it's inactive, right? Because you're ignoring it. So you ignore the constraint, and when you ignore the constraint, this is not there anymore. The optimal solution is therefore zero, right? So this is zero, right? And you also know that since this x is equal to zero, then this right here, whole thing, must equal to minus one. Therefore, gamma has to equal to zero in order to satisfy the complementary slackness. Okay? So implying that gamma is equal to zero. Now, it's very important. Like when you have an inequality constraint, you can basically figure out if you want to get rid of them or you want to keep them. Therefore, checking whether they're active or inactive is very, very important part of it. Okay. When you only have equality, it's easy. It's easy. But when you have inequality and equality, then it gets more complicated because the complementary slackness logic kind of forces you to think about this more carefully. Okay. All right. So in our last problem, this is the problem we just solved, and our solution was zero. Therefore, this is like not active, right? Because it already satisfied. However, let's see what happens. Let's see. Um, so this is not active. However, let's see if the constraint, let's change it. Instead of less than one, we're saying greater than one, right? So previously, the solution was less than, so that's fine. But now the solution is greater than. So the original zero, which was optimal solution, does not no longer satisfy the constraint. And the nearest solution, right? Zero is the previous one, and the nearest one is at the one. It's at this location, one. So when it's activated, then that's also easy because it's activated. The optimal solution is the solution closest to the original best solution. And the closest best solution is the activation line, which is one, right? So if that's the case, right, um, activate, they will push the solution. So you push the solution to the boundary of the constraint. Therefore, we know inequality constraint becomes equality constraint, telling that us that x must equal to 1. So, and therefore you also know that if x is equal to 1, right? So we know that if this is equal to 1, then this is 0. Therefore, it satisfies the complementary slackness. Okay? So remember, when you have inequality constraints, you need to check early on whether they're active or not. And by checking active or not, it will immediately tell you whether you can just ignore the constraint or you know the solution because the solution is right at the boundary. Okay. Okay. Now, you can't directly minimize the Lagrangian. Some people might wonder, like, okay, you have a Lagrange multiplier, and you convert the function from the regular constraint optimization into a Lagrangian with the Lagrange multiplier. Can you just run gradient descent and minimize this? And the answer is no. No, you can't just run gradient descent. You do need to basically go over the KKT condition for the most part. For the most part. In this particular case, right? So let's say this is an equality constraint. Well, it's not as simple, and then once we convert it, so once we convert it into Lagrangian, it's not as simple as just running gradient descent on this to minimize it, because you need to really, really constrain. You need to really, really figure out lambda. If you don't know lambda, you end up in the same scenario where you have to pick lambda over and over and over again. You will have to pick gamma over and over and over again, right? And if you pick the wrong one, let's say this is a minus, right? Or or plus 5. I don't know. If you pick something, you could really, really screw it up. So the point is you kind of can't do that. For equality constraint, what you can there's a trick. For equality constraint, like this one, if you add a square, right? And make sure you pick a number here, a value here that's positive. So let's say you pick 1, for example. And therefore, when you run gradient descent, it's going to try to make this as small as possible. So you can see that by adding a square, you can achieve, I guess, you can achieve um, equality constraint. And by picking this intelligently, you can also achieve inequality constraint. But it's a lot of trial and error. Right? You have to do a lot, and gradient descent at times doesn't really do a good job reducing them. So I would be hesitant. Yeah, yeah, yeah. For a lot of problems, um, we did. There's an entire field called optimization that basically tries to solve this. It is theoretically doable, and if you have a sufficiently powerful enough function, you could do it. But I will stick with the KKT condition for and only do gradient descent when you really have to, and you need to like do lots of trial and error as a result. Okay. Okay. So over here, we I did try to use we were I attempted to solve this, right? And then it was really really hard to find lambda and gamma. So if you want, you can step through my code and study for yourself. And when you start studying it, you will see why using gradient descent is not it's tough. It's tough. Okay, like there's how there's a lot of trial and error, right? So what I did is I calculate the gradient and I of the Lagrangian, and then I try to do gradient descent. Now NumPy provides a way for simpler problems and to allow you to solve it. So here, what was the problem? So this was the objective, like x squared. Remember, that was the problem we were trying to solve, x square. We have an equality and we have an inequality constraint. So you see, x squared, here's the equality constraint, here's the inequality constraint. Now, I don't know why, but in NumPy, they do the opposite of what I'm used to or the standard that I've done. So the standard is you want the inequality constraint to always be less than 0. That's how it's set up. In NumPy, they set up so it's greater than 0. Little minor annoyance, but just keep that in mind when you're solving inequality constraints. They set up different from the way I taught you. Basically you need to put a negative to it. And then once you set up the objective, equality, inequality constraint, you define here as the equality constraint, you define G as the inequality constraint, and then you simply call the minimization, which you minimize the objective and then you set the constraint. This is your initial. Remember how when you run like things like gradient descent, you start with some initial value. So this is your initial value, and then once it's solved, it tells you your optimal solution is -1. Okay, so this is and your optimal solution function result is 1. So this is how you will solve a lot of the constraint optimization problems um, with NumPy. Okay, so that was I think here. Okay, so here's another example. All right, this is just inequality constraint. So this is so you're trying to minimize this subject to x less than 1. Right. So remember, we like to do x -1 less than 0, but they like to do it 1 minus x greater than 0. So hence 1 minus x. Like very important. Keep that in mind. And then exactly the same thing. So this basically allows you to solve inequality constraints. Okay? All right. So for today, I want you to practice solving these problems. Okay? Problem 1, 2, 3. I think I wrote, yeah, I solved them for you, as well as the logic, as well as the code. Man, I put a lot of work into helping you guys. So, okay, yeah. So, you want to pause the video, like really try to solve them yourself. And once you've done that, see if you're able to get the same solution, right? And and if you can get the solution, verify your solution by writing your own code. Right? Once you write your own code, you will see that okay, then whatever you solve is whether correct or not. Okay, that's it for today. I think we're gonna continue with constraint optimization next class. So I'll see you later. Bye.